Question 6 from Section 2 of the 2022 Higher Physics Examination from the SQA. The Standard Model explains how the basic building blocks of matter interact, governed by 4 fundamental forces. For 1 mark in Part A, it's asking us to name the type of particle that's composed of a quark and an antiquark pair. Well, a particle composed of that quark and antiquark pair is a meson. A meson has going to get 2 quarks. One of them is an antiquark and the other is an ordinary quark. So the answer to question 1 is a meson. Part B, it says a particle known as the positive K plus is composed of an up quark and an anti-strange quark. And here's that particular particle here. It's composed of an up quark and an anti-strange quark. It says the negative K-on particle, K minus, is the antiparticle of the K plus. And state the names of the quarks that make up the K minus particle. Well, the antiparticle of the K plus will be the K minus, and you just have to do the following. The up quark becomes the anti-up quark, and the anti-strange quark becomes the strange quark. So that will be the K plus particle, and that will be the K minus particle, the antiparticle of K plus. And finally, for 1 mark, it says the W boson is the force mediating particle associated with the decay of kaons. Name the fundamental force involved in the decay of kaons. Well, the W boson is the mediating particle for the weak force, or sometimes it's called the weak nuclear force. That's your 3 marks for the first part of question 6. Question 6 continued, part C. It says another particle known as a pion, that's pi, is a product of the kaon decay. And a beam of pions travelling in a straight line at a speed of 0.95 c passes between 2 detectors, as shown, detector 1 and detector 2, and the detectors are separated by a distance of 30.0 metres. And for 3 marks, we have to calculate the time taken for a pion to travel between the 2 detectors in the frame of reference of the station observer. Well, the station observer sees the distance between the detectors as 30 metres and measures the speed as 0.95 c for the pions. So therefore, we just go back to a simple little formula to work out the time of an object which passes a distance, and time is going to be distance divided by the speed in which it's travelling at. So therefore, we just need to plug in the numbers for this one. So we'll come down here and say that time t is equal to the distance, which is going to be 30.0 metres. And we divide that by its speed, and its speed is going to be 0.95 c. So we have to put a bracket around and go 0.95 multiplied by the speed of light c, 3 times 10 to the power 8, and that'll be metres per second. You can see the metres cancel and the seconds is up to the top, so we've got the correct formula. So we plug that into a calculator, we get an answer of 1.05 times 10 to the minus 7 seconds. Now we can do a wee bit of work on that, that will still give you the right answer, but if we move the point 2 further places ahead, we can now say it's going to be 105 times 10 to the minus 9 seconds, just by moving that 2 places further to the right. So 105 times 10 to the minus 9 seconds, we can write that as 105, and we can put that down as nanoseconds. And that's our answer in the form which is the appropriate form to write this answer down. Part 2. Calculate the distance between the 2 detectors in the frame of reference of the pions. Well, if we're in the frame of reference of the pions, we're really seeing the length of the detectors moving in this direction here with the speed of 0.95 c. Think about it. If the pions are going to be moving past this way, then if you are sitting on a pion, you'll see the detectors moving in this direction here like that with a speed of 0.95 c. So the length which the pions will measure will be the relativistic contracted length, and we can easily find out by putting in our formula. The length which we measure in the pions reference frame will be L prime, and L will be the proper length, which we know is going to be equal to 30 metres. So that's going to be the proper length between the 2 detectors measured in our reference frame, and the distance measured in the pions reference frame is going to be L prime. And we know from our reference sheet, our data sheet, that L prime is going to equal to L times the square root of 1 minus V upon C, and it's going to be all squared. Now we know that it's going to be 0.95 C, so the distance measured in the pions reference frame is going to be L, 30, times the square root of 1 minus, and because we've got V in terms of C, it'll just simply be 0.95 squared. So we do that in our calculator, we get the value of 30 times the square root of 1 minus 0.95 squared. That's going to give us something like 9.37 metres. So according to the pions reference frame, they will see those two detectors rushing past them, and the distance between them will be much shorter, 9.37 metres. Question 6 continued, part D. Pions have a mean lifetime of 26 nanoseconds in their frame of reference. Explain why a greater number of pions are detected at the second detector than would be expected if relativistic effects are not taken into account. Well, there's a distance there between the two detectors, D1 and D2, and if we didn't take relativistic effects into account, the pions would have a lifetime of 26 nanoseconds. But when we do take relativistic effects into consideration, the lifetime of the pion in our reference frame stretches to 106 nanoseconds. That's almost 4 times longer than the lifetime of the pion in its own reference frame. Now, because we measure the life of time of the pion to be 4 times as much, it's going to travel 4 times as much at a given speed, and therefore more will reach detector D2. So it's all down to the relativistic working out of the lifetime of the pion. In its own reference frame, it lives for 26 nanoseconds. That will carry a certain distance. But in our reference frame, we know that the time is going to be stretched or dilated to 106 nanoseconds. And that's almost 4 times as much longer lifetime we measure it to be than the pion in its own reference frame. So that 4 times longer lifetime will mean that the pion travels 4 times as much distance between the detectors D1 and D2, and therefore they're going to be a lot more reach detector D2. Question 6, part E. The use of analogies from everyday life can help improve the understanding of physics concepts. A website states that the standard model is like a set of children's building blocks with all sorts of different shapes and sizes, and these building blocks make up all matter. For 3 marks, we have to use our knowledge of physics to comment on this analogy. And that's what we do. We think of the standard model and we compare it to a children's building block set. Well, really the analogy holds up quite well, because in the standard model we have got a basic set of particles which cannot be broken down into any other particles. These are called the fundamental ones, and they're made up of the quarks and the leptons, and they have got different sizes and different shapes. So we could in fact argue that point, that the analogy is quite true. So we can write down the first thing. We can say that the building blocks are fundamental and it can't be broken down into smaller blocks like the children's play set with the different building bricks. And also we can also put down that there are different types of bricks, like there are different types of quarks, different types of leptons, and these are different types of bricks, very like the different fundamental particles, the quarks and the leptons. And we also can put down the following from our argument. We can say from the box of blocks, different structures can be built. Just the same as you can build different things from your set of building blocks, then for the standard model you can build things like mesons and baryons. And it's good to put in what the mesons are. This gives you your mark for understanding physics. Mesons are made up of a quark and an antiquark, and you can have various varieties of those. And baryons are made up of 3 quarks, and you can have various varieties of those as well. And you can compare that with the actual building blocks that the children use. From different sets of bricks you can build up different particles. So that's our first part. We can argue with that one then. But also we have to be very careful that the model in fact is not particularly correct all the way, because the model perhaps fails. And it's good to say this because it's bringing out your knowledge of physics. The model perhaps fails because it doesn't take into consideration how the bricks join together and are kept together. We know that in the mesons and in the baryons, the quarks are held together by the strong nuclear force, and that's really arisen because the particles are swapping over, exchanging a particle called the boson, and that keeps them together. But in the children's bricks, that doesn't happen. The children's bricks are kept together by the small dimples clicking into the holes of the other side of the brick, and that's what keeps them together. So if you bring that out about the bosons and the gluon being responsible for keeping the real particles together, and not really coming through in the analogy with the children's brick set, then once again you're showing your level of knowledge of physics. So just to recap again, yes, the model's quite good because the building blocks are fundamental. They can't be broken down into smaller blocks. And there are different types of bricks, very much like the different fundamental particles, quarks and leptons. And from the box of blocks, different structures can be built, just the same as you can build different mesons and different baryons from the standard model. And you can mention what a meson is, quark and antiquark, and a baryon is made up of 3 quarks. And you also can put in a little bit of criticism here why the model doesn't in fact hold too well, because the model perhaps fails because it doesn't take into consideration how the bricks join together and are kept together. The children's structures are kept together by the little dimples going into the little holes in the bricks, but in the real world of particles, the quarks are kept together by the strong nuclear force, which is mediated by the exchange of the boson, in this case being a gluon. So if we mention all that sort of stuff, you should do well for your 3 marks.